Hello, and welcome to Agrosive Physics. Today is day 102, and what I'd like to discuss today is conservation of charge. Now, as we all know, neutral objects have no charge, and in chemistry, we typically talk about that in terms of an atom. An atom is neutral, it has the same number of protons and electrons. Now, of course, we have neutrons, which is another subatomic particle, but they don't have any charge at all. So you have protons and electrons that are basically determining whether or not an object is charged or not. So an atom by default is neutral. On the other hand, we have ions, which are charged objects, and they can have a net positive or negative charge. Well, the way this works is that the electrons, which are held on the valence shell of the atom, are being removed. Protons and neutrons, the proton itself is what makes an element an element. The neutron determines the total atomic mass and can be a contributing factor to isotopes. But in strictly static electricity, the topic of static electricity, what we need to worry about is how many extra electrons we have. Now, although we may have a net positive charge on an object, if that's the case, that means electrons are removed from the object. If we have a net negative charge, it means that the object is gaining extra electrons. Now, in chemistry, we call the charge of an electron -1, charge of a proton +1. But they actually have a specific value. And in the metric system, we need to use the value for coulombs. We'll talk about coulomb in a little while. But in terms of the charge of an object, it is measured in coulombs. Now, the value for an electron and the value for a proton is 1.6 times 10 to the negative 19 coulombs. So what we can do is figure out the total net charge in an object. In chemistry, you would have said +2 or -2. Well, in physics, we need to know the actual value in coulombs. So what we have is an equation that isn't really stated in the reference table because it's merely a conversion. And I remember it as Q equals N. Q equals N times E. And E is the charge of an elementary particle. Now that means it's either a proton or an electron, and the value's positive 1.6 times 10 to the negative 19 if it's an extra proton. And it is negative 1.6 times 10 to the negative 19 if it's an extra electron. The Q is the total charge of the object, and we can find N, which is the number of extra electrons or protons. Now, N has to be an integer. You're not going to break up the electron into smaller pieces. Now, we will talk about how we actually can do that later on in the course when we talk about quarks. But for now, we're going to consider the electron and the proton and the neutron as the smallest particle that we can have. And that's why in chemistry you discuss them as the fundamental particles, the subatomic particles that make up the atom. In fact, those particles are made up of even smaller things called quarks. And at this point, the quark is the smallest thing that we know of. Well, who's to say there isn't something even smaller than that maybe you, after you expand your science knowledge even farther, will learn about in the next 10, 20, or 30 years. So right now, we're going to look at just the electron or the proton. So if we have an extra number of protons, we're going to have a net positive charge. If we have an extra number of electrons, it will be a net negative charge. The elementary charge is 1.6 times 10 to the negative 19 coulombs. Q is the total charge on the object, and N is the integer representing the number of extra particles. Now, with that said, we have conservation of charge in a closed system. That means if we have two objects that were neutral and one gains electrons and the other loses electrons, the total charge of the system still needs to be 0 or neutral. And that's just simply stated as in a closed system, the total charge is constant. So what we can do is determine what the charges will be in different situations where charged objects will touch one another and then separate. And we're going to do a number of sample problems in the whiteboard. But simply speaking, whatever the total charge of the system is, it has to remain the same throughout the problem. And that's, of course, in a closed system. If we introduce external charges, then that will throw off our results. Now, one thing to note, since you have to have a whole number of electrons, you can't have half charges. So if you have +2 and -2, well, that would add up to neutral. But then if you had a third object involved, it would be 1, 1, and then one of the other objects would have to have 2. So maybe one extra electron on one extra electron on the other, and then 2 extra protons on the third. And the net charge of that 3-object system would still be 0. So you're not going to divide it as 1 1/3 each. It would just be 1, 1, 2. And which one gets that extra electron, it really would depend upon where that electron was when we separated them back again. When the objects are touching, the electrons are repelling each other, and what happens is, as we separate the objects, all of a sudden, that extra electron is stuck on one of the objects. But needless to say, we're going to transfer charge from one object to another when they touch because of the repulsion of charged particles. So we'll do a couple of sample problems on the whiteboard, but for now, let's discuss the object or the device, let's say, that can detect charges in and of itself. The object, the device that we use is called the electroscope. And there are 2 different types of electroscopes. Basically, you have a insulator where the charge is going to be detected, and that's so that we don't have any external forces. In some cases, it's a jar, so it's made of glass. In other cases, it will be a metal cylinder, typically. It will almost look like a bass drum, a kick drum. So what happens is, inside of a metal conductor, just like we discussed with Tesla, the electric field is 0. So you have no external forces affecting it. Now, one of the electroscopes have 2 metal pieces of foil at the bottom, and if they are charged, they will separate. So if there's a net charge, the foils will separate. Another one has an arm that will rotate depending upon the charge. So the 2 different electroscopes will detect charge by moving from their rest position. If it's one with the metallic arm, it will rotate. If it's the one with the leaves, it will separate at the bottom of the leaves because of the repulsion of the like charges. Now, the problem with the electroscope is that you can't actually determine what the sign is directly. It can detect charge, but you don't know if it's positive or negative. So what you would need to do is have a charged particle that you know, or let's say an object that you know is positively charged, and bring it near the electroscope. And then that would either cause the leaves to diminish, which means it would have an opposite charge, or spread apart, which means you'd be giving it even extra charge. So depending upon the charge that is brought near the electroscope, we can then determine what the charge on the electroscope is. But directly, all we're going to be able to do is detect the presence of charge, not necessarily the sign. Now, the strength of the charge will be relative, and some electroscopes may have a scale, but it's typically a relative scale. And as with the arm one, if it's vertical, it has 0 net charge. If it moves slightly, it'll have a small charge. If it moves greatly, that means the charge is even larger. So the amount of movement will determine how much extra charge we have. Now, with the one with the leaves, if it spreads out a little bit, that would show a small amount of charge. If it spreads a lot, that would show a greater amount of charge on the electroscope. Now, basically, we have a metallic sphere at the top. We'll have a conducting arm that leads into the body of the electroscope. The electroscope will either be made of glass or a metal sphere of some sort so that there's no external forces involved. And then what will happen is at the bottom, you'll either have the metal foil or you'll have a metallic arm that will be repelled by the straight rod that goes into the electroscope. So there's different types, and we'll discuss the different types in class with a little more detail, but I'm going to show you a few examples of them in this presentation. Charged electroscopes versus uncharged electroscopes are something that you'll be required to just be aware of recognizing, but since there's no actual scale that denotes any type of electroscope, all you'll be able to do is detect the presence of charge, and then maybe they'll have 2 different electroscopes, one with a little bit of charge, one with a lot, and you'll have to determine which one has the greater charge or something to that effect. But remember, the electrons are the only things that move. So if you have a positively charged electroscope, it means that the electroscope itself has lost electrons. when it was brought in contact with another object, the electrons on the electroscope were brought into that object, and the electroscope then loses electrons, thereby becoming a positive charge. But once again, you can't detect that directly. It has to be an indirect method of detection. Now let's look at some sample problems for conservation of charge, and then we'll discuss different ways you can charge objects tomorrow. Thank you. All right. Now the conservation of charge states that the total charge of a system is constant. So if we were to look at some examples, let's look at the following. If we have a plus 12 charge on one object and a minus 6 charge on the other, the total charge in this system is plus 12 minus 6, or a positive 6 total charge. Now remember, that plus 6 represents 6 extra protons. If we take those objects and touch them together, what will happen is the charge will distribute as evenly as possible between the two. So when we do that and separate it, we're going to end up with plus 3 on each object. So the charge will distribute as evenly as it can, and in this case it can distribute evenly. Total charge is still plus 6. Now if we want to know the actual charge on each object, what we need to do is take our plus 3, which represents 3 extra protons, and remember that each proton has a charge of 1.6 times 10 to the negative 19 coulombs. And since they're protons, it's a positive charge. We multiply that by 3. And we'll end up getting 4.8 times 10 to the negative 19 coulombs of charge on each sphere. So in this one example, the total charge stays as plus 6, but each sphere in this case will have a charge of plus 4.8 times 10 to the negative 19 coulombs. Each one will have that same charge. And this is why we stick to the plus 6 or the plus 12 or the minus 6 to begin with, because it's much more difficult mathematically to deal with the times 10 to the negative 19th term. So dealing with the plus in terms of the extra protons or electrons is going to be easier to deal with. But at the end, we can figure out the total charge on each sphere or the total charge in the system, which would be 4.8 times 2. And if we use our calculator for that, which we shouldn't need to, but 4.8 times 2 would be 9.6 times 10 to the negative 19 coulombs. Now, if we started with that value and we wanted to find the number of extra protons or electrons, we would divide that by 1.6 times 10 to the negative 19 coulombs, and we should end up with plus 6. So remember, the 1.6 times 10 to the negative 19 coulombs is the charge on one elementary particle. So it's the elementary charge. And it's listed on our reference table as E. All right, we have 3 separate examples here. We have a plus 8 and a 0. We have a plus 12 and a minus 4. And we have a plus 2 and a plus 5. So let's look at the first one now. Total charge on this first one is plus 8. And there are 2 objects. So when they combine, they will keep the plus 8 and distribute as plus 4 for each sphere. For the next one, we have plus 12 and minus 4. So the total charge in this system is still plus 8. And what you could do is write total charge, but if you write it in a circle, it might get confusing. So I'm just going to write the total charges of each of these on the top in between them. So we have a plus 8. Well, we already saw how plus 8 distributes between 2. We end up with plus 4 and plus 4. So even though we started with different charges, we still end up with the same charge on each sphere at the end, and that still is a plus 8. That's a good way to check your answers. Make sure the totals are the same. Now in this last case, we have plus 2 and plus 5. Well, that's a plus 7. Now we have two objects, and when we touch them and separate them, they'll distribute as evenly as possible. But what you have to make sure is not to make it 3.5 and 3.5, because the electrons and the protons aren't going to split up any farther. They're going to stay as protons and electrons. So what will happen in this case is we're going to end up with 7 distributed between 2. So we'll either get plus 3 and plus 4, which will keep us at plus 7, or it could happen that you have plus 4 and plus 3. Now it's hard to tell whether or not it's going to be the one on the left or the one on the right. What's going to happen is when we separate them, they're still fighting over that extra positive charge. Now, of course, remember, that means they're pulling electrons away because the protons aren't going to move at all. But either one of these would be correct. What won't be correct is if you did this, plus 3.5 and plus 3.5, because the electrons and protons are not going to distribute in half. They have to remain whole numbers. So these have to be integer values. But remember, the whole total charge on each of these is the same, and the charges are going to distribute as evenly as possible between the spheres. Let's look at some more examples now. Okay, in this situation, we have 3 spheres. We have a plus 8, a plus 4, and a minus 3. So the total charge is going to stay constant after we touch them. Plus 8 and plus 4 is plus 12, minus 3 is plus 9. So the total charge is plus 9. Now, since we have 3 objects and we're going to touch them simultaneously, when they separate, they're going to distribute the charge as evenly as possible. And plus 9 will be divided as plus 3, and plus 3. And remember, the total charge stays the same, so we have 9 on both sides. For this one, we have the same initial setup. We have a plus 8, a plus 4, and a minus 3. But what we're going to do is not touch them all at the same time. We're going to take A and B and touch them together. We're going to separate them, and then we're going to touch B and C. Now, what's important to remember is that if C is not involved with the initial contact, it's going to maintain its -3 charge. So what I'm going to do is bring the -3 here, because that's not involved with this first part. But if I look at just A and B, the total between them is plus 12. Plus 12 will be distributed between these two as plus 6 and plus 6. So now A has a plus 6, B has a plus 6, and C has a -3. Now what I'm going to do is touch B and C together. Now B is plus 3, and C is -3, so the total is positive 3. So A is not involved with this final touching, so it's plus 6 still. Now how is 3 going to be distributed between B and C? Well, it's not going to be 1.5, so it'll either be 1 and 2 or 2 and 1. And what I'm going to do for now, because we'll just go down in number, we'll say that B gains the plus 2 and C gains the plus 1. It could be the other way around, though, 1 and 2. Either answer would be acceptable. Now, with that said, if we notice the total charge on all of these setups, they should be the same. 8 and 4 is 12 minus 3. Total, plus 9. 6 and 6 is 12 minus 3, plus 9. And then finally, 6 plus 2 plus 1, 6, 7, 8, plus 1 is a positive 9. So the total charge in the whole system maintains the same value throughout the entire experience.